So yeah, I'm Sophia Brumer. I'm currently in Toulouse in a atmospheric lab. So I'm working with people that are trying to understand processes of wind gust in mid-latitude cyclones, and they hired me to look at the impacts of air-sea coupling in those systems. So this is just the slide that you already seen from Jean, that shows nicely the coupled processes that are important at the RC interface, and the ones that I had highlighted, he had added bubbles, which I should have done there too, where waves are important. So I kind of cut these lectures into two parts. The first one is going to be on fluxes of heat and momentum, and the second part is going to be on air-sea gas fluxes. And unfortunately, I won't have much time to talk about aerosols, but they're important too. So anyway, just to give you a bigger, more climate overview of why we care about air-sea fluxes of here showing you heat. It's because on the climate time scale, what's going to dictate the variability and climate change is how the ocean is going to respond, because it's has a much higher heat capacity and it evolves on longer time scales. And so it's important to have the fluxes at the interface correctly computed, so we can close the energy budget in an adequate way. And so what you see here is zonal averages of the mean heat fluxes, so it's the latent and the sensible heat fluxes. And the different curves show you different products. So there are two that are going to vary, the two black ones, depending on the bulk algorithm, so the way they're computed. And then there's an impact of the resolution. On the right here, you just have the differences plotted. And you can see that there are some major differences in the tropics, but actually also throughout the mid-latitudes of huge uncertainties. Depending on which flux algorithm you're going to use, you're going to have different ones. The bottom here is a bit of the same, but it also shows a different products data sets. So there are differences not only in the way we compute those fluxes, but also of the state parameters that we use to compute them. And there is uncertainty in both. And this leads to global huge variability. So here's the standard deviation between the different products, and you can see regions. So for the heat fluxes, where you have strong winds, where you have big waves, so where you have strong currents, that you're going to have a lot of uncertainties. And here's for the momentum flux, it just highlights the region where you have high winds. And so there, the two parts of this problem is the state variables and the bulk algorithm that is used. So here's just a table from Megan Cronin's article that went and reviewed how well we do with estimating the bulk parameters. And what I just want to highlight here is that while we're working on everything, and there are satellites to measure better all these different components, sea state is something that is not really considered properly, and there's no real requirement as what do we really need in terms of sea state parameters. So this is something we have to work on. So this slide just gives you an overview of what we mean by the turbulent fluxes. So these are the bulk formulas here. So what we measure is actually the through eddy covariance is this part, and then what the models do is this part here, where we, based on state variables, so the wind at a certain altitude and the surface currents, for instance, through a drag coefficient, we can relate these bulk parameters to the stress. So the same goes for the heat fluxes. So yeah, we're just illustrating the different platforms where we have eddy covariance systems, and we also doing it from drones lately. Wait. Oh yeah, hold on. There we go. Laser pointer. Ta-da. All right. It's fine. I was just going around in circles anyways. So the way these bulk algorithms function is that they solve iteratively for the drag coefficient, and it's based on the Molyneux-Bukov similarity theory, which assumes under homogeneous and stationary conditions that the dimensionless parameters, such as the dimensionless shear and the lapse rate, are just universal functions that depend on the z over L, and L is being the so-called Molyneux-Bukov length scale. And so this is what this theory gives you. On the different stability condition, you have different profiles, with the stable profile being the most sheared one and the unstable one the least sheared. And so integrating this, we can solve for the drag coefficient or the heat transfer coefficients. Now this assumes that we have a constant flux layer in between the roughness length here and a given height where we have our measurements, which is not true. We know that in the presence of waves particularly. So waves, as Jean already mentioned, come into this roughness length parameter through the Charnock coefficient. And so this is a slide that he's already shown you. This is how one of those algorithms, the core algorithm that's widely used, does. Now this is just the measurements, and you have to note that direct measurements don't go beyond 25 meters a second. And it does okay in the mean, but as already discussed, there's a lot of scatter in the low wind range, and this is where we have more the mature seas, and you even have negative drag coefficients, which means momentum is given by the waves back to the atmosphere. And then there's a question of what's going on here at high winds that was discussed. So I'd like to take a step back and actually talk about these universal functions of the, for instance, dimensionless shear, and they all stem from measurements over land. So from this Kansas experiment, where they did the eddy covariance measurements over cornfields. Now you do see waves in cornfields, but do they look like what we have in the ocean? Probably not. So this was the original work, and then later on, there's been efforts to measure it overseas. So here's one of the historic data set of RACEX in '95, and you can see that. So this is the dimensional shear plotted against this stability parameter, or Z over L, that I talked about before. And you can see how the data from the ocean diverges from what was measured on land. And then they continued on in another big experiment, the Sea Blast, in 2003. And you can see that, yet again, you have a different shear profile. And so what can explain the differences between these two data sets? Well, if we look at where they were taken, the first one was in the North Sea, so like off the coast of Denmark, where you have very limited fetch. And the other one is from the platform, the ACID platform off the coast of Martha's Vineyard, where you have a very long fetch. So the big difference here in both the stable and the unstable condition is the fact that you have swell or the swells. And that's not really taken into account in those bulk algorithms because they have one stability function. And so here I'm going to just show you another clear example of this. This is now for unstable conditions, and the different dots colored are depending on wave age. So red is the oldest, more mature waves. And so the solid line is what the Money-Nabokov theory would give you, and then the departures of it due to having swells or not. And so this is what the measurements give us, and there's been already work done. So this, I dug out some old LES efforts from Peter Sullivan, linked with the Sea Blast experiment. And you can see some very interesting features of swell propagating against here the winds and swell propagating with the winds. And what you see, there's a drastic difference in the profile, and when you have swell following the winds, you even have the formation of low-level jets. So all of that is not really included for the low wind part in the current bulk algorithms. So there needs to be a way to take that into account. And now obviously we have the other side of the drag curve I showed you, so the high wind conditions, and this is where we have braking. So I'll just show you a nice picture of the white capping, which has potentially also an effect on the albedo, but probably a minor effect on the global radiation budget. On the very high winds, we have also tearing off of the crest, so the sea spray, which was already mentioned by Jean, and that has a very important effect, well, potentially an important effect rather, on the momentum and heat fluxes, and also on the mass fluxes, ejecting aerosols. And underneath the water on the other side, we have bubbles, and these bubbles, especially on the high winds, are going to be important for anything that's gas transfer, which has then consequences on the carbon sink and ocean hypoxia. So I'm gonna, right. And last but not least important is that it generates turbulence on both sides of the interface. So I'm going to just do a quick review of what sea spray. So sea spray, there are different sizes of drops. The ones that are important probably for the momentum and the heat transfer are the larger drops, from which we have even less measurements, than the smaller ones that are created by bubbles just surfacing, coming to the surface. So why are big drops important? Well, once ejected, they first equilibrate the temperature. So that means that there's a sensible heat flux. And then they start evaporating. So depending how long they stay in the atmosphere, they can evaporate more or less. So that implicates a latent heat flux and a temperature feedback. Then you can also think that the fact that you have droplet loading in the lower atmosphere, it kind of creates a buffer zone. So the winds above don't feel the stress from the waves anymore, the drag from the wave. And so it could reduce the drag coefficient through that. And it can also have a huge implication on the stability. So just to quickly illustrate this, I just took out some results from this paper by Bao et al. In 2011, which shows the drag coefficient and the enthalpy transfer coefficient. So there are two curves for each. Without spray, here for the drag, which keeps increasing. With spray, he managed to decrease it. And here for the enthalpy, with spray, we increase the enthalpy. And this has consequences that have been studied for very strongly forced winds, such in hurricanes, which is what I redid also with the French research model, where you can see here just a cut through a hurricane, like an idealized hurricane. You have the wind speed. The dashed lines are without spray, and the solid lines are with different sea spray source generation functions. And what you can see is that all inputting sea spray into our model increases, as we expected, the maximum winds. It decreases the friction velocity, and it increases the sensible and latent heat fluxes. Now, the magnitude of this increase is going to strongly depend on what source function you put in. All right, so that's kind of gives you an overview of why waves are important in the heat and momentum transfer. And now I'd like to switch to the air-sea gas transfer, which is much of the same problem, really. So that shows up very nicely, sorry. The flux of gases across the interface is usually expressed in terms of a gas transfer velocity and the difference between the atmosphere and the ocean, the difference in concentration. And so we can measure this also through eddy covariance. And now we're looking at the covariance between, obviously, the vertical velocity components and the mixing ratio in dry air. Sorry for this slide. So the interesting part with the gases is that it actually happens in 3 different compartments, the gas transfer. It happens in the atmospheric viscous layer. It happens across the interface, and it happens in the ocean surface layer. And so which side is important, or which side is going to be the slowest, is what's going to control the total gas transfer velocity. So this gas transfer velocity is typically expressed into a water side and an air side resistance. And so for gases that are have very low solubility, such as CO2, also DMS or oxygen, it's whatever is happening in the ocean that is important. So the gas transfer velocity, like most air-sea interaction parameterization, are typically expressed just as a function of wind speed. So these are the traditional parameterizations that you find in climate models. So they're either quadratic or cubic. And so what I'm showing you here is eddy covariance gas transfer velocity estimates for CO2, the squares, and DMS, the circles. And you can see that above 10 meters a second, you have a huge scatter in the data. And so with each data set, each field campaign, a new parameterization was proposed, and they diverge significantly. And what does this mean? This divergence actually mean for the global, for instance, here the CO2 flux. So I'm showing you zonal averages for the different seasons with the net CO2 flux. So the different lines are the different parameterization, linear, quadratic, or like the biggest one here, cubic. And you can see that the estimates of the CO2 flux goes from 1.2 to 2.7 gigaton of carbon a year. So it goes from, it's over 100% uncertainty here. And so this is an old paper from 2002. Really, the situation hasn't changed. Maybe more parameterization have been proposed, and this is a review by Wolf in 2019 that shows again the huge variation of the net flux and the gross flux estimates depending on these parameterization that we picked. These are all wind speed only parameterizations. Just to illustrate this, again, sorry for the formatting. Just geographically speaking, what does this mean? Like the different parameterizations here, you have a difference of the CO2 flux between the cubic and the quadratic parameterization, and it highlights areas. I've highlighted areas here where the difference is important, and so this is the North Sea, and here's just off the coast of the Labrador. You have regions where you also have deep water formation, where the difference is the biggest. All right, so going back to this issue, we know that there's a lot of scatter, and we can imagine that this is where wave breaking becomes important. So as I said before, wave breaking creates sea spray, and you can assume that sea spray has an impact on air-sea gas transfer, because when it cools, it's gonna degas, and then when it shrinks in size, it's also gonna eject some gas. However, there's no measurements, and not really, nobody has spent enough time to really quantify this. What people have looked into more is the effect of bubbles, and so when bubbles get into the ocean, they just offer an extra interface for the air-sea transfer. And because of pressure, the hydrostatic pressure, there can be supersaturation in the ocean and extra outgassing for the bubbles. And then you have also Langmuir cells that can transport smaller bubbles further down, which is important for even more sparingly soluble gases or insoluble gases, including oxygen. And so I'm gonna just show you what I did. That's my thesis work based on this field campaign where the goal was to finally get measurements at high wind speed of waves, gas transfer, through gas transfer through eddy covariance. There had been other efforts previously, the GasX cruises, including the Southern Ocean GasX. But we were luckier during this high wings cruise in 2013, where we were sort of chasing storms, and we had hit quite a few along the way, particularly a very strong one, which was then the St. Jude storm when it hit England. So I got this high wings data set, and here I'm showing you the gas transfer velocity for CO2 from this data set in blue, and from 3 other historical data sets. And they show nicely the divergence that I've shown you before. At high wind speed, depending which data set you pick, you have either a cubic or a quadratic relationship with wind. So what I just did quite simply is I decided to express the gas transfer velocity in terms of a Reynolds number that combines something about the winds and something about the waves. So here's significant wave height. And to my surprise, and they all collapsed nicely on a simple curve. So with that, just adding significant wave height, we managed to have a better expression for the gas transfer velocity for CO2, and this is something that should be interesting for the climate community that still uses just a quadratic relationship for CO2. We also had another gas on high wings, which was DMS. Now, DMS is more soluble than CO2, and it shows mostly a linear dependence on wind speed. And when I plotted that against the Reynolds number, I didn't quite find an improvement, so wave are less important, and that's because the bubble-mediated transfer is less important. So these are just simplistic empirical parameterizations, but really we should go to more physical aspects of this, and as I said before, the gas transfer velocity should be described as a water-side resistant and an air-side resistant, but within this water-side resistant you have what's purely frictionally driven and what's driven by bubbles. So this is also what's done in the extension of the core algorithm for gas transfer, and where this bubble part is just a function of the white cap coverage. So the white cap coverage, the data from high wings also showed that it was nicely could be nicely parameterized by this Reynolds number that I talked to you about before. And if we implement this parameterization of the whitecap coverage in the core algorithm for the gas transfer velocities, we've had an improvement. So here I'm showing you the gas transfer velocity binned data for CO2 in blue, DMS in orange, and you see the old parameterization of whitecapping, which was the historical Moninobukov from 1980 parameterization that shows just a cubic dependence of the whitecap coverage of the wind speed, overestimated the CO2 flux at higher winds, and adjusting that with the parameterization depending on the Reynolds number, we have a much better fit, not only for CO2 but also for DMS. I then went on and decided that really the frictionally driven side of this equation, we should look into how wave breaking and wave breaking dissipation impacts the fluxes there. So I tried to express the gas transfer velocity in terms of the bubble mediated part and a turbulence driven part. And so the idea of this turbulence driven part was not new. It was something that had been looked at in estuaries and also in the open ocean with direct measurements of the TKE dissipation rate in the water. And in the bubble part, I just stayed with the same formulation that we had in the core algorithm, where we have the whitecap dependence, but we also have a dependence of this parameter, which is the bubble air volume flux, which is taken as a constant mostly because we don't have that many measurements. But as I'll show you, there have been some developments there where we can express it as a function of this breaking crest length distribution. So this breaking crest length distribution is stems from a framework that allows to link surface, so parameters of the length of the breaking and the speed at which it propagates to different characteristics of the momentum flux, the turbulent dissipation rate in the water. So this allows you to estimate the TKE dissipation rate from images, which is what has been done in the past. So these are historical data sets, and here you have the high wing breaking crest length distribution, which don't quite match what was done before. And however, to link, so this the fifth moment of these breaking crest length distribution to the TKE dissipation rate, you still need a breaking strength coefficient, which there are different approaches to this. In a group with Zappa, we had work on trying to parameterize an effective breaking parameter as a function of the wave age. So this is what I've used to then compute the TKE dissipation rate. So that was for the turbulent part of the gas transfer coefficient, and then for the bubble mediated part, I said I wanted to include have a varying bubble air flux. Bubble air volume flux. And so this I've based on the work by Daike et al., who did some DNS simulation and showed that the void fraction, or the volume of air entrained, can also be related to the breaking crest length distribution. So this is quickly to show you that we can come up with just pure wave breaking parameters to a model that does pretty much as good a job as the core G model. So here what you have is the measured gas transfer velocities for CO2 in purple and DMS in this reddish color, and the modeled one on the y-axis. Here you have the core G algorithm with this kind of the basic, and then my model, which doesn't perform too badly. There's been obviously more work with this kind of approach, where we try to include more about waves into these gas transfer parameterization, and Daike and Melville, and then taken again by Reichel and Daike, came up with a simplistic formulation with a non-bubble mediated and a bubble mediated part, and the bubble mediated part has some dependence on the significant wave heights. And what they did, Reichel and Daike, is compute that over a longer time period over the whole globe, so we can look at the impact of including significant wave height in the gas transfer velocity does. So here they just show you snapshots in climatology of the wind speed, of the significant wave height, and then of the gas transfer velocity they compute with their simplistic mechanistic model. And you can clearly see that you have the strong storms, wind systems, with high significant wave height, they're also associated with very strong gas transfer velocity. Now, the gas transfer velocity doesn't give you the whole story, because obviously you have, for the flux, you need to take into account the fact that you need to take the concentration into account, and so you have some disparity that are not linked to waves because of the difference in the concentration. And so what you see here is the picture of the global CO2 fluxes. There are regions that are highlighted where you have a clear sink of CO2, and there's also the region where you have a higher percentage of the bubble-mediated transfer, which you see here. So in the higher latitudes, you have a very strong impact of high winds events and breaking events, where you have that importance of the bubbles. And so basically, they showed in their paper that the wind speed over 17 meters a second is a good proxy for showing where the bubbles are going to be important. This is what is illustrated here. So this talks about the fluxes at the surface, but really when we talk about carbon, the carbon pump, or even ocean hypoxia, we're interested in how from the surface it then goes further down, and this is where waves can be important again, and this is through the Langmuir circulation. And so this idealized model by Shiba and Bacek showed the importance of Langmuir bubbles and Langmuir circulation. So here I'm just going to show you for the different gases. You have the gas exchange rate. So these are the Vanninkhoff is the classical gas transfer parameterization that is in the climate models currently, and then you have the model that they proposed with Langmuir and without Langmuir, and so this is the gas exchange rate, and here is the percentage of how important are the bubbles on the Langmuir cell for each of these gases. So you can look for oxygen. You can see that above 10 meters a second, you have bubbles that start becoming important. At already 15 meters a second, they account for 20% of the total flux. And you also start having Langmuir circulation that are important. Now for CO2, it's clearly mostly bubbles, and Langmuir circulations seem to be less important in terms of bringing the bubbles down. However, they are important when you think about the mixed layer depth and the complete carbon pump, because obviously deep water formation and bringing the water down, high CO2 water down to the deeper depth is going to depend also on the mixing. And this is just to illustrate this quickly, where we have regions where we have the deep water formation and the deep mixed layer depth. Here is for the winters in both hemispheres. These are from observation. This is from an ocean run where we don't have Langmuir circulations and mixing in there, so we don't we have biases in those regions, and then there are different ways about going about this. It's just to illustrate that if we input something about Langmuir mixing, we get something closer to reality. So just to wrap it up, I've hopefully given you an overview of why waves are important and how they modulate or drive even air-sea fluxes of mass, heat, and momentum. And this is via bubbles and sea spray. And I've tried to highlight that we do take them into account to an extent, but still very crudely. And so that we really need to take them better into account, because they have a huge impact on the wind profiles in low winds, but also in high winds. I didn't show you, but that was something that I took out from the conference we had in Reading, is that sea spray not only has impact on the winds, but also on the rain. And this is work by Shui and Benjamin Barr. And then obviously that it has, so this is more the local impacts, and it has also impacts on the climate timescales in terms of the global energy budget, ocean energy budget, and also of the carbon pump, and potentially for ocean hypoxia. So thank you.